250 years ago, we began to build in microgravity. Not high up on some space station or on the moon, but right here on Earth, using towers very similar to this one. By understanding how these incredible structures work, we can get clues as to how we will colonize the solar system and bring the final frontier right to your living room. The purpose of the Coop's shot tower, located in Melbourne's CBD, was to produce small spherical balls of lead, much like these ones. When used in hunting, hundreds of these pellets are loaded into a cartridge, so they need to be extremely cheap to produce. Regular manufacturing techniques just aren't up to the task. Machining would take too long and is far too expensive, while casting isn't accurate enough. So if these don't work, how do we do it? That's where a shot tower comes in. Today, the folks at Ballantine Ammunition have agreed to show me how this works. We're really lucky today because this is the last shot tower still operating in Australia. About 3.5 tons of lead is melted inside this massive container, high up at the top of the tower. Unfortunately, lead fumes are pretty toxic, so if we were melting today, then I'd be wearing the safety equipment. Our molten lead gets pumped out of the tank and poured through this sieve. The holes are precisely the right size in order to produce the type of lead that we want. As it passes through the sieve, regular manufacturing ends and microgravity manufacturing begins. When you spill a glass of water, gravity pulls the water molecules downwards, causing those below out and forming a puddle. By removing gravity, the internal force of surface tension is able to take control. It wants to bring everything as close together as possible, which is why when an astronaut spills some water, it forms a perfect sphere. The same is true for molten pieces of lead falling from a tower. By incorporating microgravity into the manufacturing process, this tower produces over 1 million pieces of lead shot every hour. All of this is possible in just 3 seconds of freefall. Now that access to space is getting more affordable, what new materials might we be able to create? The answer to that question lies within this building, the old stock exchange. Back in the gold rush era, you could buy and sell shares in different companies. If the company that you bought, say a gold mine, happened to strike a particularly rich seam of gold, then you could stand in to win a lot of money. Of course, while a lot of this is luck, there are some ways to cheat the system. Here's how it works. You put a really fast runner up in Bendigo with instructions to come and tell you if anyone finds gold. If they do, it's you who'll know this information first. So you can buy lots of those mining stocks, and when everyone else finds out the information, the price of those stocks will increase, giving you a guaranteed profit. At the beginning, this is working out pretty well for you, but then your neighbour Bruce catches on to what you're doing. He buys his runner a horse. Now he's making all the money. In response, you buy a car, he buys a helicopter, you buy a fighter jet. It's an arms race of who can transfer information the fastest. Fibre optic cables are made to transfer data from point to point as quickly as possible, but the technology is limited by the need to add repeater stations every 50 kilometers or so to keep the signal strong enough to get from end to end. This adds in a small but noticeable delay. So what if we remove the need for these repeaters? Z-band fibers might be able to do this by using a combination of elements which allows the signal to be transmitted with barely any loss in power. However, this eclectic mixture makes forming the glass fibers here on Earth impossible. Gravity pulls the heavy elements downwards, which in turn push the light ones up. This promotes signal-blocking crystallization. Forming these fibers in microgravity means that we can make a perfectly homogeneous substance without any of these imperfections. A single cable of Z-band fiber could send a signal from Melbourne to Perth without any repeaters in only 14,000th of a second. This is relatively easy to do, and we know it works. There is already a module on the International Space Station producing lengths of this fiber for use in medical imaging. A journey that started centuries ago, and a tower much like this one is taking us to the stars. This has been James Dingley from the Atomic Frontier. Keep looking up.